Okay, so you pull out your phone, you open up a map, and there it is, that little blue dot showing you exactly where you're standing on planet Earth. I mean, it really feels like magic, right? But it's not. It's actually one of the most incredible feats of engineering humans have ever pulled off. So come on, let's pull back the curtain and see the amazing science that makes it all work. So, how on earth does this little device in your hand pinpoint your location with such crazy accuracy? I mean, anywhere in the world. Well, the answer is this stunning collaboration between some seriously advanced tech up in space and, well, fundamental physics right here on the ground. Yeah, you can really think of it as a symphony of three key things, all working in perfect harmony. You've got a whole fleet of satellites orbiting way up high, clocks that are just unimaginably precise, and, get this, some seriously mind-bending physics from Albert Einstein himself. So let's break it all down, and we're going to start with those satellites. All right, first up, we've got the Global Positioning System, or what we all just call GPS. Now, this is a network of about 30 satellites that are just constantly circling the Earth. And honestly, the best way to picture them is like super precise lighthouses just floating up there in the sky. And each one of these satellites is basically just shouting out into space, over and over, broadcasting this really simple message. It's like, hey, I'm Satellite X. This is my exact position at this very moment, and this is the precise time I sent this message. And your phone? Its only job is to listen in. Okay, so your phone is listening, but how does just listening to these signals tell it where you are? Well, it all comes down to a really clever bit of geometry. Your phone is basically solving a puzzle in real time to find your exact spot on the map. Imagine this. You're in a huge open field. One satellite signal hits your phone and says, hey, you're, let's say, 12,000 miles away from me. Okay, so that puts you anywhere on a giant sphere around that satellite. Not very helpful yet. But then a second signal comes in from another satellite. It creates its own sphere, and now those two spheres intersect to form a perfect circle. Getting closer. But when that third satellite signal comes in, its sphere cuts through that circle at just one single point. And boom, that's you. That's your location. So this whole process, it has a name. It's called trilateration, and it's really the core mathematical trick behind all of GPS. See, your phone measures the tiny amount of time it takes for the signal to travel from each satellite. And since we know that radio waves travel at the speed of light, a constant, it can instantly calculate its distance from each of those satellites and, do that whole three-circle thing. But of course, there's a little catch. To get a really precise location, I'm talking about your altitude too, you actually need a fourth satellite. Think of this fourth signal as like a master check on the system. It's there to correct for any tiny timing errors because your phone's clock is, let's face it, nowhere near as good as the ones on the satellites. And that whole issue of timing, well, that turns out to be the real secret ingredient to this entire system. Seriously, the entire GPS system lives or dies on timing. And I don't just mean good timing, I mean unbelievably precise timing. Because these radio waves are traveling so incredibly fast, even the tiniest error, a fraction of a second, can throw your location off by miles. So how do you solve that problem? You solve it with atomic clocks. The atomic clocks on board each of these GPS satellites, they're just masterpieces of precision. So how precise are we talking? Well, they are so accurate that they would only lose about 1 second every 300,000 years. Just try to wrap your head around that. It's a level of accuracy that's almost impossible to even imagine. Okay, but why does that much precision even matter? Well, think about this. If the system's timing was off by just a tiny fraction of a second, the error in your location would grow by about 10 kilometers. That's 6 miles. Every single day. Your map app would be completely and totally useless. The bottom line is this. Without these clocks, there is no GPS, period. But this is where the story gets truly wild. Because even with these perfect atomic clocks, there's a problem. A fundamental problem of physics that would bring the entire system crashing down. And it's a problem that could only be solved by the theories of Albert Einstein. Okay, so stick with me here. The GPS satellites are moving incredibly fast. We're talking 14,000 kilometers per hour. Now, according to Einstein's theory of special relativity, that incredible speed actually makes their clocks tick just a little bit slower. But they're also really high up, way out of Earth's strongest gravity. And according to his general relativity, being in weaker gravity makes clocks run a little bit faster. So you've got these two weird competing effects going on at the same time. So, what happens when you put those two effects together? You might think they'd just cancel each other out, right? Nope. Turns out the effect from weaker gravity is just a little bit stronger. The net result? The clocks on the satellites actually run about 38 microseconds faster every single day than our clocks down here on Earth. And that tiny, tiny difference, 38 millionths of a second. Does that number sound familiar? It should. It's the exact amount of error that would cause that massive 10-kilometer drift every single day. So the engineers who built this whole system, they had to literally account for Einstein's theories of relativity. They deliberately designed the clocks to run a tiny bit slow here on the ground, so that once they're launched into orbit, they tick at the absolute perfect rate relative to us. It's incredible. Without Einstein, GPS would simply not work. Now, your phone isn't just sitting there passively listening to all this. It's an active player. Especially when you're, say, indoors or in a dense city where satellite signals are weak, it's got other tricks up its sleeve. It'll check for nearby Wi-Fi networks, it'll triangulate its position using cell towers, and it even uses its own internal motion sensors to guess where you're going between GPS fixes. It's a total team effort. So when you zoom all the way out, you realize this isn't just some clever invention. It's a global utility, something we all depend on every single day. You've got dozens of satellites, ground control stations scattered all over the planet, and billions, with a B, of receivers in our pockets and our cars, all working together 24/7 in this perfectly synchronized dance of physics and engineering. And get this, it's not just for getting directions to the nearest coffee shop. That hyper-accurate timing signal coming down from space, it's like the hidden backbone of our entire modern world. It's what synchronizes bank transactions. It's what keeps our power grid stable. It helps emergency services find you when you call 911. It even guides tractors on farms for super efficient agriculture. It's everywhere. A system like this, it didn't just happen by accident. It is a perfect example of intelligent design. And I mean human intelligent design. It required scientists and engineers to anticipate the bizarre effects of relativity, to build clocks with almost impossible precision, and to launch and maintain this perfectly coordinated fleet of satellites. Every single piece had to be purpose-built to work together flawlessly from the very beginning. So the next time you glance down at your phone and see that little blue dot, maybe just take a second to appreciate what's really behind it. It's not magic. It's a testament to human ingenuity, a beautiful, invisible symphony of satellites, atomic clocks, and mind-bending physics, all working together in harmony just to let you know exactly where you are. Kind of makes you wonder, right? What else in our daily lives works on such a mind-boggling scale, completely hidden in plain sight?